All right, so I hope everybody can see the screen. Well, before we get started, I want to just go over very quickly what does HFWorks integration inside SolidWorks mean, and this seamless interface with SolidWorks. So if you get SolidWorks, essentially you get the standard SolidWorks interface. This is where the CAD geometry can be built. And one of the challenges, obviously, for RF engineers is to work with realistic CAD. And in this case, I'm just showing a simple part. So this is actually a coax to waveguide transition. The real product and what mechanically has to be built is the entire part. What needs to be actually simulated is the air inside. And being in SolidWorks, you'll be able to do this. You don't have to simplify or develop another model of different geometry or any of these things. So if this were the example, or I'll show a little bit later another type of example which is also realistic, you do not need to do anything to the geometry. You work with the full assembly, with the full CAD. In essence, even if you have screws or a very high level of detail, you don't need to worry about it. This is one of the main advantages you'll have by going with HFWorks. So, assuming the geometry is built and completed inside SolidWorks, HFWorks is a simple add-in. It's a gold certified add-in. It's just going to add this tab here with all that you see in here. That is where you'll be able to carry out your simulation. It is also accessible through the Tools menu, and you'll see it being added into SolidWorks in this manner. Okay, so it will show up as an HFWorks add-in, and to give you all these menu items where you can do a number of things. It will also come up and add this ribbon here, this ribbon bar, where you can do a number of HFWorks commands. You can access them through the ribbon bar as well. Now notice that the connection between SolidWorks and HFWorks is straightforward. Whatever you call your assembly here, it shows up with the same name in this case. Okay, and once you have the geometry and the geometry is ready, that's where you start doing the simulation. And this is the part I'm going to go over briefly today. But the way I'm going to do it, actually, I'm going to go about it in a slightly different manner for first-time users and people who are not familiar with EM simulation. I'm going to show you how you can do this using a built-in tool to actually get two models quickly and easily. So I'm going to close this document. I'm not going to save any of this. So this is SolidWorks when you get it, and if you've installed the add-in, HFWorks is going to show up here. Now I don't have any study open or any model open. So as a first-time user, you could simply go to the help and just go through the demo viewer. And this is, I'm going to use the demo viewer to actually show you how you can do, you get some stuff done. For first-time users and to even for more advanced users, you can find a number of options through the demo viewer. So the demo viewer is essentially ships with the product. It installs on your machine, and it will come with the standard shipment of examples in antennas, in resonance, and in S parameters. Okay. You can also define your own user examples and user-defined models and examples. You can put them in this demo viewer, browse them, and open them and manage them through the demo viewer. Okay. So the demo viewer also comes with a search capability. So if you're, you want to do something like maybe, let's say, you want to do a microstrip or a printed something, while it's going to filter. Okay, printed. Okay. So right now it's showing me everything that's printed in the antenna. So all of these antenna printed examples, they're printed antennas. I can open any of these. So you have the capability, obviously, to do the search. Otherwise, these antennas are grouped in different types. If you're interested in planar antennas, those are some of the examples. If it is more of a waveguide antenna, there are a couple of examples that are already there. horn antennas and the types. And if you are doing a wire antenna, there is an example of a wire antenna there. And these are being continuously updated and augmented with new modules every time. So to illustrate an antenna example, I'm going to go to the user, and I'm going to use this. Actually, this is a slightly a different model. This is a horn antenna which has been twisted. Okay. And this is, again, to illustrate the power of the coupling between SolidWorks and HFWorks. Okay. So if you try to build this model here of this antenna in any non-CAD package, you basically will be out of luck. The only way you can do these kinds of things in a powerful CAD packages, and SolidWorks is the #1 CAD package right now for PCs, and you're able to do this type of stuff inside of SolidWorks. Okay. So let's say this is the antenna. Obviously, we added the air part to it. So if you look here, I have the base of the antenna, this flange that connects the antenna. I have the tilted horn, which is the metallic part of it, and I have the air part, which is what's inside in everything else. So if I right-click here, I can actually isolate this part. I can just look at the air only. So we can see here that this is the air that's inside. This is the computational domain. Okay, this is what we're interested in. But the mechanical part and the actual product is everything else around. So let's go over into HFWorks and very briefly illustrate how we would study something like this. So you would come and you say, I want to study this. And in this case, I might want to do, obviously this is an antenna, so I want an antenna type that's antenna simulation. Here you control the solution parameters. So the default parameters is that you use the multi-core direct solver, which is a parallelized solver that will take advantage of the CPU that you have and the multi-core capabilities. The default meshing order or the accuracy of the solution, use higher order mode, higher order elements. And then you can do a number of other things. You can do parameterization. You can skip 3D solution and look only at the port solution. And you can enable or disable adaptive meshing. Okay. And the default is that we don't enable adaptive meshing because if you know what you're doing and you can use some of the features we have for meshing, you can get to your solution rather quickly. In this section, you control the frequency settings, whether you do a discrete sweep and simulate at each frequency, or you can do a fast sweep and get a frequency response on a large number of points quickly. Here you decide your start and stop frequencies. If you want to do, in this case, maybe it's actually 1 to 2 or 1 to 3 gigahertz. This is okay, and you decide on the number of points if you want to do any number of points in a discrete sweep. So if you wanted to have like maybe you can also put a step if you wanted to go to 0.25 every 250 megahertz, then it will fill the frequency table for you. You can ask it to compute the far field parameters, or you can just look at the input impedance first and the matching. So if you do the far field parameters, you can decide on the far field resolution in terms of the elevation and azimuth angle, the number of steps. So in this case, the defaults are 10-degree steps in theta and 15-degree steps in phi. So this is where you decide what the simulation parameters are going to be. You can give it a name or take the default name. It's called the study 2. And when you click OK, then you have a structure of the simulation or a study. There are 3 steps that need to be performed. We need to define the materials, we need to apply the boundary conditions, and we need to do the meshing. Okay. The meshing step is optional because if you just do the first 2, then you can, if you ask it to solve the problem, it will mesh using the default meshing parameters. Okay. So let me illustrate very briefly how we would apply the material. So in this case, I have the air part, okay, in any of these parts. So the horn is actually made out of some material, of copper in this case. So I can just, it's in part of my favorites already. So I'm going to say this part is copper. Okay. And it will say, tell me already that that's copper. The air part is actually air, so it's part of my, and this, the third part, the base, is also copper, so I already have copper here, so I can just drag the copper and drop it here. So I have 2 copper parts and 1 air part. There are a number of other ways I can do this as well. So let me very briefly show you if I create a material folder, okay, and I make this material out of metal. Let's say this is it's going to be my copper or bronze or whatever. So I'm going to say maybe let's pick something different. So it's just bronze. Okay. So anything I want to be bronze, yeah, well, these 2 instead of being copper, they could be bronze. So I can just select them and drag and drop them, and they became bronze just like that. Okay. If this air part were another material, I can go back to my material library. This is my material library. I have a number of different things. We have cable, ceramics, semiconductor, substrates, and so on. So if this were a substrate material from Rogers, this is a hypothetical, obviously, just to illustrate how we do materials, then you can just say, okay, this is a Deroid 5880 material, and the dielectric, the properties that are actually come directly from Rogers are applied there, and you just say that, and then that part becomes Deroid. It's that simple. Ultimately, you also have an option that if you wanted these metallic parts, you don't want to include them in the simulation, you could just drag them from here and exclude them in the material folder. We have that option as well. So lots of flexibilities in how you do materials, very efficient ways to group things, to exclude things, to drag and drop, and so on. So that is the first step, the materials. Now the boundary conditions is another important step and is required before you can solve. So in this case, we have essentially the key boundary conditions is that this surface here is going to be a port, the entry, that's where the energy is coupled. And this outer surface is essentially an artificial truncation of air. So it's an artificial boundary condition. It is a radiation boundary condition or an absorbent boundary condition. So these are the key ones. Where the air touches the metal, we need the boundary condition as well there. But that one we don't have to do because we already told the material we have metal here, so the solver will know that there is a metal-air interface and will apply the proper boundary condition there. So really, the only 2 boundary conditions I need are the port and the radiation boundary condition. So I'll illustrate how we apply a port boundary condition. So I'm going to clear this selection, and I want to go and select this face here, and this is essentially a SolidWorks standard feature. So we look for the surface here, and then when we click it, I can eventually preview it to say that, is that the right face? And actually, it's actually not the right face. So I need to pick this entry surface here. So I can say pick other, and look at this. That's the face I want. If I preview that, that's my port, and I'm happy with that, so I say my port is defined. If I had multiple ports, I can pin this, and then apply this, and then pick another surface, and then that's going to be my port 2. In this case, I only have 1 port, so my port is added there. Okay, I go back. The next boundary condition is going to be this one, the radiation boundary condition. Okay, again, it's surface selection, so it's a multiple surface in this case. And this is trivial. Again, you can preview this selection, and it tells you, yeah, that's that's my absorbing or radiation boundary condition. That is done. At this stage, the model is really set for simulation. I can create a mesh, and in I can just make a coarser mesh or a finer mesh. Okay? Or I can actually control the mesh parameters manually. Okay, you see as I do this, and once I say okay, it's going to go and mesh the model for me. So those are really the key steps. One of the reasons why we might not use mesh adaptation is that we have a feature called mesh controls. Okay, so let me illustrate what mesh controls gives you. Well, mesh controls allows you to define specific mesh sizes to control, make the mesh coarser or finer on different bodies. So this is if we had to apply mesh controls to a body, to a face, or edges. And this is critical because at high frequency, edge controls are very important. Okay, so you don't waste elements on volumes. You can just concentrate elements on edges that are important. So if I wanted to select a body, let's say I want to select this body here, okay, but actually I don't want the body itself, I can extract the faces of that body and I want to apply control to those faces. Okay, I can clear the selection, I can go back to the body, select this again, but actually I don't want the faces, I want just the edges of that body. So I can get all those edges that make it that body and say, wherever I have an edge, I can apply a boundary condition, or I mean a mesh control to those edges. I can select which ones I want to keep, which ones I want to delete, and so on. So this is a very, very powerful feature. Makes the meshing and the number of times you need to create a mesh or adapt reduced significantly. So we gain a lot of time by taking advantage of this. Okay. So if that's the selection, this is the control parameters. You want to say that on these edges, maybe I want a 10 millimeter element size as an average size, and so on. And that will create a mesh control for me in my meshing tree. Okay. So when I go now and create mesh, it's going to take into account what I instructed it to do the mesh finer at certain points. So this is very briefly the process of doing setting up study. It's very similar whether we're doing antenna simulation or as parameters or resonance, but that is the process. So if I were to say run at this stage, the solver is going to mesh first and then execute the program and get me the antenna parameters and generate results. So I've already run this study, okay, and I'm going to show you what a simulated or a completed run study is like. So first, let me show you the mesh. So you see that here we meshed only the air part. Okay, the metal is no need to mesh the metal, so we didn't need to mesh that part. So that's what my mesh looks like. I'm going to hide that in Legoma. And then once I solved this problem, and in this case, if I look at the properties, I did a single frequency solution. I looked at 2.82 gigahertz. Okay, my results folder is created. This study doesn't have a results folder because it was not simulated. It was not run. Okay, and then under results, you have a number of things you can do. You can look at the port fields. You can look at the electric parameters, and then you can look at the electric field and magnetic field throughout the volume. So let's see some of the plots that have been generated. You can generate as many plots as you wish. So I have a resultant electric field plot, okay, so shown in section. So I did essentially a section plot on the electric field inside this antenna and how it's propagating. I have also created the vector plot of the same thing. So I can see the vector plot of the vector electric field going in, and I also have done an isosurface plot. Okay. Any of these can be animated, okay, either versus phase, in other words, as versus time, or we can animate it versus time at a given frequency, or at different frequencies. If I've done multi-frequency points, it's going to just get the solution from each frequency and animate versus. So in this case, I'm going to animate this versus time, versus phase, and we can see that this level of field is going to reach up to here, and then the field is going to decrease as 1/r, okay, and it's going to propagate that way. If I look at if I show this plot, which is the section plot, and then animate the fields versus phase, then I can see that now I see my radiation, how this antenna is behaving. Yeah. So you could do that. The electric field, you could do the same thing to the magnetic field. You can generate 3D field plots. You can also generate 2D field plots. So you can just interpolate the field along a line inside the model and see the values of the field as a 2D plot. And I'm going to probably show you this in another example a little later on. The electric parameters is where you get your results table. This is where you get your antenna parameters, your S parameters, the gain of the antenna, the directivity of the antenna, and so on. You can also look at your port results. What's the propagation constant, the impedance at the port, the VSWR at the port, and so on. So this antenna is working pretty well at 2.82 gigahertz, and that's something that you've seen. Okay. And you've seen that from the propagation, obviously. The last step, the last thing I want to illustrate with this particular example is the report generator. So you can go and generate reports once you've completed. You can put a logo here, put the name of the author and the company, and you can date this report, and you can generate it in HTML or in Word. And this is the content that you want. So if you want to put a cover page, if you want to write an introduction, you can write something right here. You can add some description. You can choose or not to have the file information. The model views, it comes with a current view and an isometric view. You can pick any other view. Let's say I want a top view of this and without the mesh, and you can add. So you can put as many views as you want in there. If you want material information to be included, you know, study properties, anything you don't want, you just, you know, uncheck it, and there you go. Okay. And once you're ready, you say, okay, I'm going to generate this report, and it will, instead of you doing cut and paste and print screen and all of those things, it's just going to go and capture everything that you've created, any plot that's created, and put all of these in a Word document. And once it's done, it will open up the Word document, and this it will open it up inside of SolidWorks, so that you, again, no need for you to be changing between applications or switching between applications. The whole process can all be run within SolidWorks. If there are any questions, you know, please feel free to type them in the chat box, and then try to answer them as we go along. All right. Okay. So let me see if I can. Okay, let me see if I can pick another example to illustrate more of these capabilities that are inside HFWorks. Okay, bear with me a second here. Okay. All right, so my next example is going to be a PCB, a printed circuit example of a filter. So let me see if I can get filter example. All right, so as my model opens up, I'm going to show you, this is a typical filter for people who are active in the PCB area and they do PCB design and so on. So here I have essentially a multi-resonator coupled filter, okay? And one of the challenges of these filters is that they are, the meshing is an issue because the fields are, again, concentrated and they're very rapidly on the microstrip structure. So again, as I showed earlier, the process is doing studies. In this case, it's an S parameter study. So if I look at this this S parameter study, I can look at the properties of it to see what we've done. So we've essentially done a fast frequency sweep between 2 and 3.5 gigahertz, and we've done 300 points. Okay, and that's how we solved it. That's our list of frequency points and so on. And so in this case, we have a substrate material that's an R4 material, and we have an R part that is hidden, so I can go ahead and show that part which is covering the substrate, or I can hide it again and focus on my printed filter. In terms of boundary conditions, I have a couple of ports. That's my port 1, and that's port 2. And then obviously I have a PEC ground and the printed filter. So those are my boundary conditions. My mesh. I think that my screen is visible.
We can see it now.
I'm sorry about that. I think my screen was off for a brief little while. So very briefly, again, this is my substrate. I have an air part that was hidden, so I'm going to show it very briefly. My ports are port 1 is on this side, and port 2 is in this side. So these are microstrip ports. My conductors are the ground plane, and a top conductor, which is the printed filter itself. I'm going to hide my air part because I'm going to focus on the filter structure per se. The meshing, again, I explained before, we do mesh control, so we can control the edges of the surfaces of these. Okay. So if I show the mesh here, then we can see that I have a very fine mesh where the field is going to vary, but then my mesh is essentially very coarse as I go away from those. Okay. So when you do S parameters, obviously you're interested in the S parameter plots. So in this case, I can do a 2D plot of S parameter. I'm going to add S11 and S21, have 2 plots, and generate my plot this way. So we can see here, this is my filter response as computed by HFWorks. This is the 2D plotting. You can do a number of things with this, obviously. You can do the listing of your data. You can put markers, you can, at any given point. And you can do a number of other things. You can export data if you want to use it in a circuit simulator. You can do printing. And obviously, you can, the curves and a number of other features that we can do with respect to the plot properties. If you wanted to change the colors, the thickness of your traces, and all kinds of things, obviously, it's very, very reconfigurable, very powerful 2D post-processor for the results. You can obviously also look at this in a Smith chart format, so you can look at your data in the Smith chart, and you look at your matching over frequency. In this case, I'm looking at this S11. And the same kinds of things, the printing, the listing, the multiple curves. You can bring other data from other measurement or whatever and superpose it on this. Lots of features for productivity with this tool. What we've done, what we explained with the electric field plotting, you can do the same thing, obviously. So if you look at your response, this filter is a pass band around 2.6 gigahertz. So if you wanted to do a look at what's happening to the electric field at 2.6 gigahertz, then you could just go and pick the resultant electric field and plot the field. In this case, I have the field plots at 2 gigahertz, so I can just show that, and they can animate and see what's going on at this frequency for this filter as we change the phase. So the same kinds of things that we've talked about with respect to the antenna in terms of post-processing, section clipping, ISO clipping, all of those things are available, and you can do them as well here. The reporting, all of the other features, again, are available in here. Okay, so my last quick example, again, I'm going to go back to my demo viewer and maybe go into parameters and maybe pick some kind of a coaxial, maybe take a connector, for example, and look at coaxial transition with TDR. So if you wanted to do examples where you do TDR, okay, Lots of people work with connectors and so on. Again, very easy inside SolidWorks, making assemblies and complicated stuff in geometry. We handle all of that here. And this is a coaxial transition that needs to be 50 ohms. Okay, and folks who do coaxial transitions and are very interested in looking at TDR. So the field plots and all the stuff that I already talked about is there as well. In this case, for TDR, we need to look at the impedance as a function of time. So again, very briefly, to do TDR calculation, we need to check this compute TDR option, and here is where we define what we're looking for. We're looking for the response, a signal rise time of 0.05 nanoseconds and a maximum duration of 500 nanoseconds, and with a number of points that's 400. If you define your time domain parameters, then the frequency domain calculations is automatically defined, and the software goes and does a frequency simulation and gets the S parameters over the wide band of frequency, and from that S parameters computes the TDR. So the TDR plotting works the same way as the other plotting. You can go pick which parameter you want from which study, and in this case, if you want to add the impedance or the voltage or the current, you can just add, and then you say, give a title. I already have impedance 1, let's say, for example, and if you click OK, then it goes and gets the data for you. And you can see here that this is a pretty good design, because your transition is there, and there is a slight drop in impedance as you go from port 1 to port 2, but then essentially it's a 50 ohm design, and that's really what you're after. And you can do parameterization of this. You can do to get the best design. You can play with a number of parameters. So let's say, for example, if I wanted to look at these materials, and I'm looking at first body has a dielectric constant of 2.1, the second one has a dielectric constant of 3.5, and the middle one is 1.4. Let's say you wanted just to see what if I picked the material that's instead of 1.4, 1.5 or 1.6. It's very simple. You drag and drop this one here. It will make a copy of it. It will copy everything. So I don't have to redo any of those other steps. I just go to the material here. I'm going to go edit material, and then I'm going to just change this dielectric constant to 1.6. Okay, and say OK. And now the results are invalidated because they don't correspond to the materials that were set. But I'm essentially ready to run this problem and see what happens if I change that material. It's that simple, that easy. All right. So I'm going to close with a very quick last example, which again shows the power of SolidWorks, the combination of SolidWorks and HFWorks. And this one is essentially it's going to be an S parameter, a filter, okay, a multi-cavity high-order waveguide filter, where we have tuning screws. And this could be a headache for people who make filters. How do we make models that will simulate multiple screw positions? Well, this is where the combination with SolidWorks is very handy and is very powerful, because what we do, we take advantage of a feature called multi-configuration. So what essentially we have done is we have these features, which are essentially screws coming in, which kind of become holes in the model or piercing. And for each configuration, okay, we give parameters that we say the depth of this configuration is going to be a certain value, and we call that a design or a configuration. Okay, so by default, if I show the without screws, this is what it would look like. If I didn't put any screw anywhere, the model is going to look like this. Okay. But if I wanted to say screw number 1 is at 1.5 millimeter, the other one is at 1.3, and so on and so forth, then that's a different configuration. Okay. So what happens to S parameters? What happens to the filter response? That's the question. So this is where, again, the power of HFWorks and combination with SolidWorks comes in very handy, because you can generate multiple studies, and each study will be associated with a configuration. So I have a study without screws, I have a study with one configuration, study with another one, and I can generate as many of those as I want. I can do the process of materials, boundary conditions, and meshing, and I can run them all with one command, run all studies. Okay. So in this case, if I look at my data, okay, this is the response for this configuration. I can go very quickly and easily and say, okay, I'm going to edit definition of this, but I'm going to go to the first study, study 1, which is a different one, and I'm going to add the S parameters from that one, S11 and S21. Okay, and I say, okay, and now I'm comparing two studies. Okay, without screws, which is study 1, and this, my study 2, which is essentially where I put screws at T1.5, 1.3, and so on. And I see how my filter response is shifting around. Okay, so this is very briefly another feature that illustrates the power of HFWorks and the combination with SolidWorks. And with that, I will stop here and take any questions and hand it over to Adam.
Yeah, thank you, Omar. So we're on wait for some questions. In the event there's no questions, we'll just end this webinar. So we'll give it a minute or two.
I see a question here about imperfect materials and boundary condition and so on. That's a good question. So let's go here. For example, if I click here, I see that all of these outer surfaces are treated as perfect electric conductor. What if I wanted to give an imperfect boundary condition? So actually, if we look at the list of boundary conditions that we have, we can do wave port, we can do a lumped port, we can do lumped elements, and so on. And we can also do imperfect electric conductor or lossy electric conductor. So if I wanted to say that certain surfaces are not perfect electric conductor, certain bodies are not, so I go here and say, let's say this surface and this one and this one and this one and this one are not perfect electric conductors. Okay? Then you can say, okay, fine. Then what is the surface conductivity? And this is where you say if it is made of certain material, you need to know your surface conductivity and the surface roughness. And the software will take into account this kind of boundary condition. So it is possible to simulate those kinds of things as well. All right, other questions? Okay. So there is a question about resonance. So I didn't show actually I didn't show any examples of resonance. So let me go very quickly. Again, demo viewer has a lot of information. So I'm going to just pick an example. Let's say one of these, sophisticated or complicated resonators. So this is a cavity resonator. And I'm obviously interested in resonance and the resonant frequencies and the resonant modes and so on. So in the resonance, what we do, it's a similar process, but if you study their study properties, essentially what you're looking for is not a frequency response. You're essentially asking for the resonance modes, and the resonant frequencies. So here is where you specify what you're looking for. So in this case, we're looking for the five lowest free resonant modes for this structure, okay? And without any low frequency gas. So if I wanted to do that, and that's what this study did, I can look at my mesh very briefly and see, that this, is a decent mesh for this structure. And the results for this are, are tabulated here. Okay. And for these kinds of things, this is the important stuff. So what are the resonant frequencies? So this one's going to resonate at about 0.66 gigahertz. There are a couple of modes that are about at the same frequency. This could be degenerate modes. and the higher order modes at higher frequencies, obviously. And notes that we compute the Q factor for these for the structure. In this case, there is no dielectric; it's air fill. So the only Q is coming from the conductor losses, and you can obviously look at the loss density, the total loss, and all of those things in the results part of this. The modal field distributions and so on. All of this is available, and you can do again the same kind of things that I illustrated earlier with the antenna example. So I hope that answers that particular question.
Okay, are there any more questions, Amar?
Well, there is somebody's asking what is it that we're seeing next to the study. Okay, so this is another feature that we have for people. We have the ability to add comments. Okay, so you can insert comments at any time. It's another way to document the work and to remind yourself what it is that you've done or that you're doing and so on. So in this case, my comment on this study is essentially this comes from the demo viewer. So users who open this will see, okay, that this is a model of a resonator, and that this study is looking for 5 modes using the multi-core direct solver, and this would take roughly 21 seconds to solve. So the user who's using the demo viewer will have an idea ahead of time what is it that they will be doing and what is it they will be looking for. Okay.
Okay, I guess with this, I mean, yes,
yeah,
one more question?
I see one last question about PDF support. There is no PDF support currently in the reports section but obviously if you do you generate a report with Word, and you can just simply use the Word capability to convert it to PDF. It's a straightforward, save as kind of feature, and it will allow you to save your model, save your report in a PDF. So in this case, if I generate a report, the report comes inside of SolidWorks. This is my report viewer, and if you go to File and you go Save As, and you can pick, and then if you say I want to save it here, then you can save it as a PDF file, and that will take care of it. Okay, and this is my PDF of this is the PDF Acrobat, and this is your back inside SolidWorks. Your model is here, the results are here, the report is here.
Okay, are there any more questions? Do you have any more questions to answer, Amar?
I think I've covered pretty much all the questions that were raised.
Very nice. So thank you all for attending this webinar. We'll send you a recording of this webinar. If you have more questions, please feel free to address them to sales@imworks.com. I'll be more than happy to answer them for you at any time. Thanks all, and have a good afternoon now. Bye-bye.